Okay, let's get started. So in this video, we are going to learn about the variances. Okay, this is gonna be the short session. Okay, so the variance is simple. There are two formulas here. Okay, the first formula is e of x minus ex squared, or the second formula is this one. Okay, so nothing interesting here. Okay, so let's go to the next slide. Property of variances. The first one is that variance is var x greater than or equal to 0. Because what? Because from the definition, we have equal to e x minus ex squared. Because this one is non-negative, so the expectation of the non-negative must be non-negative also. Okay. If x is bounded, so variance of x must be bounded too. Okay. Variance is equal to 0 if and only if there exists a constant c such that probability at x equal to c is equal to 1. Okay. So how do we expand it? If probability of x equal to c is equal to 1, and then variance of x is equal to 0 is easy because one value variance is 0. But if variance is 0, what does it mean? That means x is equal to mu, and that mu is the c. That explains the other direction. Okay. For constant a and b, let y to be a linear function, and then variance of y is a squared variance of x. Because what? For the definition, we have ax plus b minus aex minus b. Okay. And this one is going to be a squared ex minus ex squared. This one is variance. Okay. Next property. If x and one thing else independent, if they are independent, so this one, variance of the sum is the sum of the variance. The reason is simple. Because what? Because let's say if we consider x1 plus x2, right? So the variance of x1 plus x2 is gonna be what? Expectation, okay, of x1 minus ex1 plus x2 minus ex2 and then square. Okay. So we can distribute the let's say the square, right? x1 minus x1 square plus x2 minus x2 square and plus 2 x1 minus ex1 x2 minus ex2. That's when we are going to use the independence. Okay, so for this one it will be x1 x2, okay, minus x2 ex1 minus x1 ex2 plus ex1 ex2. If we plug it into expectation, so everything is gonna be 0. This sum is gonna be 0. Okay, so we remain with these two terms, with this one and with this one only. Okay, if they are independent. Okay, and this one is the same concept. Okay, that's the corollary. The first example is an investment portfolio. An investor wanted to construct a portfolio consisting of shares of one or both of available stocks and possibly fixed rate investments. Suppose that two stocks have random rate of return R1 and R2, okay? Because if we are talking about the stock, no one knows exactly what the return could be, okay? No one is aware, but do not know exactly what the return must be. It is not a fixed income securities, okay? So the R1 has a distribution of mean of 6, variance of 55, and then R2 has a mean of 4 and variance of 28, okay? Suppose that first stock costs $60 per share, second costs $48 per share. So the portfolio will consist of S1 shares of the first stock, S2 shares of the second stock, and S3 share invested in a fixed asset. So the return is the expectation, right? The expected return. So I write the expected return of the portfolio is this one. The coefficient are this one. Okay? Suppose that R1 and R2 are independent. Okay, so the big caveat here is that this assumption, okay, this assumption mostly, okay, mostly not true in finance. Because usually the two stocks are slightly and positively move together, okay? But we need this assumption because we do not define how do we characterize two things move together. Or if you know some basic statistics, we haven't defined the correlation yet, okay? If we define correlation yet, we will relax this assumption. But since we have not defined the correlation in this class, so we assume this first, okay? Then the mean the variance is equal to this one. Okay? So look at this diagram. So we have S1, S2, and S3, right? Let's say we do not consider S3. We consider this one. So how do we split the funds, okay? Split the funds, okay? Into these two. Let's say proportion Y invested in S1 stock, Y minus Y in S2 stock. So the Y is the key variable here. And then because we invested in this and we could get the mean and the variances. That is what? That is the Y. Determine the mean and the variances. That's why sometimes, okay, sometimes we see that with the same mean, we get, let's say, the two portfolio here and here, right? So we could get something like this one. So there is not one-to-one correspondence between the mean value and variance yet, because the key variable is Y. Y is the input. Then Y is the output, so nothing guarantee this. But the thing that we could say in finance is that, okay, is that this one is a mean, is a variance. The investor, okay, the investor will not choose this one. So what does this portfolio represent? For example, look at this dot. Look at this dot and look at this dot. That is, if we invested in this dot, we get some mean and some variances. But we could get the same level of volatility, but get more expected return by investing in this one, right? However, if we are satisfied with that mean, we can lower the variance. This one we can lower, this one is the mean increase the variance. So that means no investor, no risk-averse investor will choose this one, but we choose along this line. So this line is efficient because we could not get better, okay? So this one we say that it is the efficient portfolio, or sometimes we say that it is the efficient frontier. Okay. So let's look at the second example, the variance of the binomial distribution. Because x is a sum, right? And we know that they're independent. This is important. They were independent. So we get this one into this one by the assumption of independence. So in exam, okay, in exam, if the calculation you made rely on the assumption of the independence, say it, okay, say it, because it's not true in general, okay. So usually the variables are not independent usually, okay. So there are some, let's say, special cases. So you should specify that assumption also when you write the exam, okay. So we get this one and we get this calculation, okay. So the next concept is the interquartile range. The interquartile range is another way to characterize the variances, okay. So that is, let me draw the picture. That is, if 25% of area on the right, let me say this. That's one 0.75, right? So what is this number? It's a quantile function, right? Remember in the chapter 3, f1 minus 0.75. And how about this one? F minus 1, 0.25. Okay. And look at this example. In last class, we have seen that the Cauchy distribution doesn't have the mean, right? So the variance could not be defined. But how can we characterize the spread? So we use another definition of the, let's say, the interquartile range. So we have to find the f, big F of x first, okay? It's the arctan, okay? And then we plug in, okay? We find the inverse, okay? And we plug in 0.75, 0.25, and we get 2. Okay, that could characterize the spread too, in case that if the mean are not defined and then the variance are not defined. Okay, but if you want to characterize the spread, this one is a good option too. So, in the end, we have seen mean, variance already. But can we go to the third, the fourth, and fifth, and let's say the moment? In other words, how can we generate the moments? The answer is straightforward. The moment generating function. So if you are interested in this, stay tuned and we will see you in the next lecture.